Okay. Okay. Hello. Welcome to another live session for the RL course. So I have my plan for today for the 1 hour is first I'll uh, maybe try to discuss the tutorial session that I had floated last week. So we'll discuss the solution. We'll go ahead with that. Uh, After that, I'll do a quick recap of what has been covered till now in the week 3 lecture. And then in the end, we finish it off by solving the non-graded assignment questions. Okay. So I hope I can cover all this in 1 hour. And okay, so let's start with the code for the multi-arm bandit that I had floated in uh, last week, last week's live session. Okay. Okay, share. I should share this. So if you want, you can view this from your PC as well. Put it in the chat. Okay. Yeah. So we just do a quick recap of what has been done in the multi-arm bandit problem, and I'll also show the solution. So you start by importing all the necessary libraries. Okay. And then you have a description of what the multi-arm bandit is. Then there is a proper visualization of all the different probability distributions that has been taken and how we want to proceed ahead with that using the epsilon greedy algorithm. Okay, so here what I've done is I have taken like 4 different distributions. One is the Gaussian, second is the uniform distribution, third is the Poisson distribution, and fourth is the beta distribution. So what I've done is I've randomly sampled two two I have 8 arms, and the first 2 arms follow the Gaussian distribution. Second, like the third, fourth follows uniform. So fifth, sixth follows Poisson, and seventh, eighth follows the beta distribution. And I'm just randomly sampling the parameter points for all these distributions, 2 of each, and then this true means contains the true mean value of all the distributions that I have. So this is the small q value. Is the true absolute true value of these distributions. Okay. So yeah, the numbers are chosen arbitrarily. There is no particular ordering or significance of that. And for real world problems, the true means this won't be available to you. Here, U means the agent. So uh, the agent has to get some estimate of the reward that it is trying to optimize. And then here, since we know the parameters as well as the distributions, we can analytically calculate the true means. Okay, so what we do is since we know all the true means, we just do an analytic calculation. So we have a function that is the pull MAB function. So if you pull a particular arm, you get the associated reward, which is corresponding to that distribution. Okay. So analytically, what they have done is they have pulled each arm 1,000 times to get a big enough sample for estimation and plotting. So what they've done is for each arm, they have pulled each arm 1,000 times, and whatever reward that they got, they have stored it in this array. Okay. So after you do that, you see that uh, if you have pulled each arm 1,000 times, you get a nice table between the true mean and the estimated means. Okay, and you see that they are close by. Uh, so since what you have done is a brute force thing, okay, you have pulled each arm 1,000 times. You don't want to do that. You want to maybe you want to try to minimize the number of arm pulls and maximize the rewards that you obtain. Okay, so yeah, uh, after that, what you do is you just plot the distribution of what you have till now. So you have sampled 1,000 points, and then you plot the corresponding histogram over here. Okay, so you see that the histogram sort of matches with the distribution that we wanted to from which we have sampled our initial true mean. Okay, so this orange line is the estimated mean, and the green line is the true mean. Okay, and you see that they're pretty close enough. in this analysis. And now what you want to do is we would like to implement the epsilon greedy and the softmax on the Gaussian bandwidths. Okay. So in the previous exercise, what we had done is we had sampled different probability distributions and did an analytical comparison. Okay. So now this is a function which implements the epsilon greedy algorithm, right? So here we have taken I've taken the number of arms to be 5. This is a Gaussian bandit. Okay, so if I pull the arm, I select the arm, and based on the mu and the sigma of that arm, I get a corresponding reward. Okay, so here the sigma has been fixed to be 1. So all bandits have a variance, a standard deviation of 1, and the mean basically varies. Okay, so what you do is this is the epsilon greedy algorithm. So how do you do that? You first do the Q estimate. Uh, you initialize all the Q values to be 0. Okay, and then you keep a track of the number of times each arm has been sampled. Okay, so basically what you're doing is you're uh, storing list of 5 lists to store to store the sequence of the Q estimates for each arm over time. Okay, so this is the Q of all arms over time. Okay, so you're storing a list of all the 5 lists, and you initialize you initialize the rewards. I mean the list of the rewards that you want to store for each corresponding arm, and the regret list. And the code goes like this. So I'm looping it 2000 times. So arm is equal to np dot argmax of q. Initially all q is 0, right? So it is the argmax of q if np dot random rand is greater than epsilon, else I do some random. I select a random arm. Okay, so this is a epsilon greedy strategy. Okay, so I have an epsilon value. The epsilon value uh, is a parameter to this function. So if I select a random number, a uniform random number, and if the number is greater than epsilon, I do exploitation. Otherwise, I do exploration. Okay, and then increment the sample count of the selected arm. Whatever arm I have selected, I increase the count, and then when whatever arm on selecting that arm, I get the corresponding reward from this pull mab function. I append it to my reward list that I have, and then I do a stochastic average of the Q estimate. So this is the current reward minus Q arm divided by the total times the arm has been pulled. Okay, so and then after that uh, you store each Q estimate in the corresponding list of this Q of all times over time. Okay, and then you return Q rewards and Q of all arms over time. Okay, and this is the function for the epsilon greedy algorithm. And then what you do is you fix some seed values. You basically generate the mu values or the mean for the Gaussian distribution. 5. If I have 5 number of arms, I do np dot random dot random num arms. So which means I'm selecting 5 random mu values. Okay, and then I run the epsilon greedy algorithm. Okay, so what I do is I run it for a bunch of different epsilons. So epsilon is the parameter. I run it for epsilon equal to 0, which is the greedy strategy. Then epsilon 0.01, and then for epsilon 1. So this is 1% exploration. This is 10% exploration. Okay. And then what next I've done is I'm plotting the convergence of the Q estimate over time. Okay. So this is a function to plot everything. Okay. So this dotted line for each arm is the true estimate of the reward. Okay. And the solid lines is the evolution of the Q estimate over time. Okay, so so this is the plot for plot for epsilon equal to 0. This is for the greedy strategy. Okay, And similarly, you can do the plot for epsilon equal to 0.01. A bunch of uh, you have a bunch of nice looking plots. So these dashed lines are again the true value, and the solid line is the reward estimate that the agent is maintaining. And then lastly, you do it for epsilon point 0.1. Okay. Now you see, this was this is a proper analytical study of the uh, epsilon greedy strategy. Okay. Now you want to evaluate the average behavior of the epsilon greedy. Okay. So when you want to evaluate the average behavior, you use the average over several runs. And similar to the earlier task, the true means are drawn from a standard normal distribution. Okay. However, the generated true means here are different for each independent arm. Okay. So the the true means are basically random for each independent run. If I'm doing it for multiple number of times, okay, for multiple number of runs. So for run number one, the true means for each arm is different. Then in the second run, the means change and so on. Okay, so this is I'm trying to basically evaluate the average behavior. This the earlier example was I have fixed the set of the true means and then did a comparison. Now we want to do an average test. Okay, so again you have a plot this function for plotting the average reward graphs, and then if you you see here now the mu's are actually being put inside the for loop. Okay, so initially this muse was out this variable muse was outside the for loop. Now it's inside the for loop, and now this is how the average reward for the epsilon greedy algorithm looks like. Okay, so uh, as expected, the greedy strategy is obviously a bad strategy because there is no scope of exploration. With slight increase in the exploration in this case, if I take epsilon to be 0.01, which is 1% exploration, I get better performance than the greedy algorithm. And with epsilon 10%, I get uh, somewhere in between. Okay, so this is uh, this is basically something that you need to analyze for different mu values that you have. But yeah, the general consensus here is that with slight increase in exploration, you expect to improve the performance. But again, if you increase epsilon to be very high, let's say 80 or 90%, then you expect worse performance because you are not actually trying to exploit the learned behavior of the arms that you have so far. Okay, so this is the epsilon greedy average reward over time. Then task three was to implement the softmax algorithm. So again, for softmax algorithm, you initialize the Q estimates, initialize at 0. This time sample keeps a track of the number of time each arm has been sampled. So here in this case, you don't need to store the sequence of the Q estimate over time because uh, we are not trying to demonstrate the convergence of the Q values now. Okay. So one optional exercise for you guys would be to observe the difference in the convergence of Q estimate over time for different values of the temperature. Okay. So everything has been commented out. So what you do is for T in range 1000, you first take this exploration exp probability, which is e to the power q by the temperature parameter. And the probability is this thing divided by the sum of all the exp probability. And next, what you do is you must first generate a random number, and you basically see if the cumulative probability is greater than the random number, you pull that arm. Otherwise, you don't pull that arm. It's basically you're sampling from the distribution that you have, and then based on that, you increase the count of the times each arm has been pulled. You on pulling the arm, you get the reward. You append that, and then do the stochastic averaging of the Q value. And now this thing is evaluated over independent runs. Okay, so the mu values change inside the for loop here, and here what we are varying is the temperature parameter. So you have temperature to be 0.01, 1, 0.1, 1, and 5. Okay. And if you plot, you see something like this. Okay. Yeah, this is the last part. Yeah. So you see some sort of a behavior like that. So you see with a high temperature value, you are basically reducing, you're getting worse performance. So while you decrease the temperature parameter, you are basically improving the softmax algorithm. So the beta parameter controls the sensitivity of the algorithm that of the softmax algorithm. Okay, so this exercise just shows the average behavior of the epsilon greedy algorithm and the softmax algorithm. So I think this was all that I had floated out for week 2. If you have any questions, you can feel free to ask me. I have shared this in the chat, and I'll also put the solution in the description of the YouTube video that I'll upload, and also in the presentation folder that you have access to. So this will be available to you all. So yeah, I think we can end this here, and now we'll quickly go to a recap of what has been covered in week 3 so far. And let me know if the screen is visible. Uh, okay. I hope you guys can see the screen. Okay, I'm assuming you can see the screen. If not, you can just stop me in between. Okay. So yeah. So I'll just do a quick recap of what has been covered in week 3. So for those of you who are joining new, my name is Manav Mishra. I'm a PhD student at the ECS department from IISER Bhopal. And if you have any doubts, or if you want to just say hi, you can contact me in this email ID. Okay. And cool. So the first thing that Professor covered in last lecture was policy search. Okay. So what policy is? Policy is nothing but policy is the is a function that maps from states to action. Okay. Its policy is a mapping from states to action. So it is defined by this value, is defined by this quantity pi t of a. So this index t represents that the policy changes with time. So this basically means that pi t of a is nothing but is the probability of selecting action a at time t. Okay, and so initially, I mean, previously what we have been doing since week 2 was that with the epsilon greedy strategy, with the UCB strategy, with your softmax and different algorithms that you have seen, uh, we have been trying to we have been trying to maintain an estimate of the reward function that we have, and based on that, we are trying to optimize the actions that we select. Okay, so now we are doing something different here. Instead of storing the reward estimates, what we are doing is we are directly playing around with the policy. Okay, so we don't have a q value here, or rather we directly take some initial guess or assumption about the policy pi, and then based on the optimization or the algorithm which we'll see about policy search and policy gradient, we directly update the pi t value. Okay, so yeah. So to start with a simple example, for policy search, let's say we have a binary bandit. Okay, so this binary bandit has a reward of either 0 or 1. Okay, and yeah, so I have basically two cases. Okay, so first is if reward rt is 1, and second case is if reward rt is equal to 0. So how the update looks like for rt is equal to 1. So if reward is 1, then my pi of t plus 1 given action for selecting action at is And okay, so this update is similar to the kind of update that we have been doing. We had been doing the stochastic update of the in the Q value part. So the basic idea for this update step looks something like this. So you have okay, this line. Okay, refer to this line. So you have the new estimate is nothing but the old estimate plus the step size, then the target that you want to reach minus the old estimate. So difference between the target and the previous estimate times some step size that you have. So here in this case, the step size is alpha. My old estimate was pi t 80, and in this case, pi t a star, a bar, a prime, sorry. So this a prime is not equal to a of t. Okay. So So AT is the action that has been that I select at time t, and A prime is are all the other actions that hasn't been selected. So the update state looks like this. So if my for the selected arm, I want my target is that the probability of getting R1 is 1, and for others the probability of getting a reward as 1 is 0. Okay, so this simplifies to this quantity here. Okay. So this is for RT is equal to 1. And if I take my RT is equal to 0, the update step becomes the other way around. Okay, so here the step size parameter is beta. In the first part, it was alpha. Here I'm taking it to here. Professor had taken it to be beta. I'm just following the same notation. And so you guys understand it why this got flipped when RT is equal to 1, why this is happening, and when RT is equal to 0, why this is happening. If not, you just remember this line over here, whatever is in this box. This should help you understanding the update part in this research. Okay, and yeah, so some interesting properties come out if with the different alphas and the beta parameters that you have with the step size parameter. So if you have alpha is equal to beta, then you have something known as LRP. Okay, this is the linear reward penalty setting. That means if like that means whatever if I take the correct action, I get a reward of 1, and if I select the wrong action, then I equally penalize my agent. Okay, so this basically correlates the two parameters. So if you look here, if I set alpha and beta to be same, this means these two are correlated. If I select action AT, then it is getting updated in the positive direction, and the other policies get downgraded. Okay, and if alpha is much greater than beta, then you have something known as LR epsilon P. Okay, so this is linear reward epsilon penalty. If I take the correct action, I give it the similar reward that I was giving it in the earlier case. But if I select the wrong action, then I don't penalize it by large amount, but by some epsilon amount, so that next time I'm more cautious and I don't repeat the mistake. So usually this is useful when you have when you want to do a task when the uh, probability of getting a positive reward is lesser than the probability of getting a negative reward. So in this case, you get this kind of a setup so that you don't want to accumulate penalties over time. And over time, when you get the reward, the probability is low. So that basically hinders the learning part. Okay. And third part was when you select beta to be zero. Okay. And that is known as linear reward in action. Okay, so here you don't penalize the wrong action, or rather you don't take any action in this case. Okay, so this basically is useful when you have something known as a sparse reward setup. Okay, I think my screen is stuck. No, it's not showing whatever I'm writing. Just a second. Okay, yeah, this is a bit of a delay. Yeah, okay. Yeah, so what do we mean by sparse reward is that whenever the probability of getting a reward from the environment is very, very low, then this kind of setup works. So you don't want to penalize when you're not getting reward r equal to 1. Rather, you don't do anything because the probability of getting r equal to 1 is very, very low. So you don't want to unnecessarily accumulate a lot of penalty, and that basically gives that affects your learning. Okay, so this was policy shell. A quick recap. Then next we have something known as policy gradient. So the idea here is that the policy that you have, you basically parameterize it. You parameterize the policy by some parameters, some set of parameters, which we'll call as theta. It could be either the preference like we had in the softmax function. You instead of the q value, you basically prefer it over the different theta values or the different parameters. So you can replace it by theta 1, theta 2, and so on, depending on the parameters that you have. Or in other case, it could be the weights of the ANN that you have. So if you want to uh, like transform the problem into deep deep RL kind of a problem, so the parameters can be thought of as the weights of the artificial neural network. Okay. So here, uh, one important quantity to introduce that was introduced to us is eta of theta. Okay. So this is basically nothing, but uh, it basically tells me that how it gives me the information about the evolution of theta with time. Okay. So in this case, it's the expected payoff or the expected reward that I uh, get. And if I write it in its discrete notation, it is the sum of all the a's for q star a pi of a. Okay. And the policy gradient update happens as such. So what I'm trying to do is I'm trying to update the parameters which represents the policy. And if I get the optimal parameter, the optimal parameter is theta star, then whatever policy that I have will be the optimal policy. Okay. So this is the idea. So what I'm trying to optimize here is uh, this quantity. Okay. So this is how the update looks like. So this step is known as gradient ascent. Okay, this is similar to what you might have encountered in machine learning when you perform supervised learning in your regression problems. But instead of moving in the negative direction of the gradient, here we are moving in the positive direction, mainly because the objectives here are different than what we were doing in your regression problem. Okay, and if you were to represent it diagrammatically, it should look something like this. If this x-axis represents my theta and the y-axis represents my eta of theta, the evolution function, then if it looks something like this, so I start with some initial estimate of theta, which is theta 0. Okay, I compute the gradient and then move in the positive direction by some amount, alpha. Okay, and then get my corresponding new theta 1. Again, take the gradient and then move further ahead. And eventually you should get to the optimal theta star. Okay, this is the idea behind the policy gradient method. And yeah, so okay, so the idea here is that usually you don't have access to this quantity, okay, because this quantity has this q star of a. So since this is a true mean and this is not something that the agent has access to, that means you don't know this underlying value. So the question comes, how exactly then do we do this update? Okay. So if I don't know my eta of theta, how do I know my gradient of, how do I calculate the gradient of eta of theta? Okay. So the math looks something like this. So I can write my eta of theta as like this. And then what I do is we do a simple mathematical trick. So we multiply and divide by the policy. Okay. The only assumption here is that the policy is non-zero. So you do a multiplication and division. And then what you have is this new quantity. Okay. So this new quantity now can be written as expectation of with respect to policy pi. Okay, and since I want this expectation, I can only get this expectation when I do when I sample the arms. And if I sample the arms, so this expectation can be approximated by this quantity. Okay, and RT, RN. Okay, so this is the quantity that I need, and if I gather a decent number of samples, I can closely estimate this expectation value, and based on that, I can get my eta of theta. And once I know that, I can easily update my theta parameters. Okay, so you see the issue here is, that you need to basically sample a bunch of this data points in order to estimate this expectation. You need to sample this quantity uh, a bunch of times before we estimate this expectation over here. Okay, so this can be thought of as some sort of a batch update for the policy. So you understand why we are calling it as batch update, because we need sufficient sample in order to estimate. Okay, Ashwin has a question. In the case of MAB, can policy gradient converge to the optimum? I think this was a question, right, in week 3 assignment. And so what? Yes. So what do you think in this case? What should be the answer? If yes, why yes, and if no, why no? I mean, technically, I'm not allowed to discuss the assignment solutions because professor had told me that not to reveal this thing. But okay, I can discuss this. So your intuition is that it should converge to local optimum, but
So
can't.
let's strike out the question itself, right?
Okay.
Let's rephrase it in this way.
Okay.
Stochastic gradient techniques,
Mm-hmm.
I know that they can reach the global minima or global maxima in the case of gradient ascent, but
Okay.
it may not reach. I mean, local minima or local maxima, but it may not reach the global maxima, right?
Mm-hmm.
So,
Okay.
I had an issue with the question itself. I'm not sure if I'm allowed to say that.
Okay.
So, the question doesn't necessarily say that if it is a local optimal solution or a global optimal. So,
Okay. In the question.
yeah, so it's kind
Okay.
of ambiguous. So I
Okay.
marked yes, which
Okay.
is unfortunately incorrect.
Yeah. Yeah. Okay.
Right. So then I googled the question and found that professors' assignment solutions were posted in CSE,
Mm-hmm.
IET, and thing.
Mm-hmm.
And then the same argument came out that it can converge to local optima, but not global optima. So the
Okay.
question could have been put in a better way. That's what I was getting at.
Okay.
Maybe I'm wrong, right? Maybe optima means global optima, but
Yeah. Yeah. I think optimal solution here means the absolute best solution that you have. So
right. Okay.
yeah.
Okay.
So
So the crux of the gradient, stochastic gradient techniques is that it can reach local optima, right?
it can reach local optima, and it may be possible that it gets stuck in that local optima. It depends
Right.
on the parameter, the step size parameter that you have. It's
Okay.
similar to the problem that you
Gradient
deal
descent
with
techniques.
stochastic gradient descent. Okay.
Right. Okay.
Oh, good.
Good.
Okay. Okay. So you see that thing which we saw in policy gradient previously was some sort of a batch update. Okay. So to see some sort of an incremental version of there, or or rather I should say an incremental update. So a new algorithm was designed. This algorithm was called the reinforce algorithm. Okay. So the reinforce algorithm works like this. Okay. So yeah. So this quantity here is equal to this thing what we had previously. Okay. So I can represent this as this quantity here. And then what new thing that these guys are doing is they're introducing a new term, which they call it as the reinforced baseline. Okay. So the idea here is that this baseline doesn't necessarily depend on the action that has been selected. And it also doesn't drastically alter the expectations that you're getting previously and the expectation that you get now. But it turns out that this quantity here helps in convergence stability, and therefore by just doing a shift in the baseline that you have, you get uh, some update. You get this update term, which you can do an incremental update, and by doing that you expect to reach the same policy gradient update that we had seen in the previous step. Okay. So you see, the idea here is that in an expected sense, in this update, uh, the gradient will be in the right direction. So this was the main contribution of the author who introduced this reinforced algorithm. So he's saying that by uh, adding this term and doing this update in an expected sense, you are still your gradient should still be in the right direction. Okay, so this is the general idea behind the reinforce algorithm. But turns out that this algorithm is extremely slow because of the high variance. Okay, because at each step your sampling random, you're sampling the rewards and doing the update, and that basically you're sampling this quantity, right? You're sampling this quantity, the expect, and the issue here is that because you're sampling only one point, you can have high variance, and due to this, the convergence is extremely slow in this case. Okay, so this was all about the reinforced algorithm. Uh, Next, we quickly look at the contextual bandits. So contextual bandits is basically an idea that sort of is more of a theoretical idea that uh, basically looks that basically sees is can be thought of as a bridge between the multi-arm bandit problem and the full RL problem. Okay, so you can think of it either as the extension of the multi-arm bandit problem or simplified version of the full RL problem. So it's an in-between stage. After that, we move to the full RL problem. Okay. So what happens in the multi-arm bandit problem is you don't have a notion of a state. Okay. So the agent has a bunch of actions. It selects the actions based on the Q value estimate that it has, and it gets a reward and so on. But in contextual bandits, what it does is it also takes into account the state the agent is in. So it introduces the notion of a state. It considers the states and the action, and based on that, it considers the state it is in, and based on that, it takes an action and gets a corresponding reward. Okay, so this way it can be thought of as an extension of the multi-arm bind problem. And the other way around, the way you think of it as a simplified version of the full RL problem is that in the full RL problem, the difference is that the agent can take multiple consecutive actions, and also in cases the reward information is sparse. Okay, so here since it's a banded problem, you have an immediate RL setting again, but in the full RL problem, it may so happen that the reward that you get is sparse in nature. So this is the difference between full RL and contextual bandit. So this is, you see, an in between stage between MAB and the full RL problem. Okay, so with this we quickly summarize what has been covered in the full RL problem. And yeah, so in the RL problem, you have an environment, you have an agent. The agent take action AT, which influences the environment. So environment on taking action AT, the agent moves to state S of t. So agent is at state S of t. It takes action AT. It moves to state ST plus one, and the environment evaluates the action that it has received, and then it sends a feedback by means of a reward. Okay, and this is how the state transition looks like. So this is what we call as the full RL problem. So you have a notion of a state, and the reward is not immediate. There can be delayed rewards, and can also be sparse. Okay, so we quickly look at the different components. So first is the reward. So the idea is a reward typically in reinforcement learning is a scalar value. It is outside direct control of the agent. It should be bounded so that we have an estimate uh, on the learning that we are doing. If actually we are learning or not. If we don't have a bound on the reward, then we won't be able to figure out whether we are moving in the right direction or not. And last thing is it should be frequent. Frequent in the sense that it's not sparse. You mean I mean for each particular for each for one or let's say some small number of actions that you have taken, we get some frequent feedback that basically pushes us in the right direction. Okay, yeah, so this is all about reward. For policy, here in full RL, this course typically looks at the stationary policy. So stationary policy is something like this. So my pi of t plus 1 is equivalent to pi of t, which is pi. Okay, so this is my stationary policy. By that, what we mean is the parameters in the policy. So if I have a Gaussian distribution, I have two parameters, the mu and the sigma. So these two parameters don't change with time. These parameters are fixed, so the policy is fixed. But the yeah the mapping uh, yeah the mapping is same. It's stochastic, but the parameters don't change as such. So that this is what we mean by stationary policy. Okay, and yeah. So next we look at the value function. So value function can be classified as into two parts. First is the state value function. Second is the uh, action value function. Okay. So state value function basically is represented by the letter V, and it estimates how good it is for agent to be in state S. Okay. So if I am in, let's say, uh, okay, if okay, so if I am in let's say state S, I should use some color. Okay, so if I'm in state S, I select some action A, and let's say A A1. I select some action A1. I move to state S prime, and then I move to state S double prime by selecting action A1 prime, and so on. Okay. So what this quantity basically measures. Okay. Hmm. Sorry, just a second. I think screen just froze. Okay. Okay. Yeah, you see what this quantity measures is the goodness of the state. Similarly, the action value function can be said, can be thought of as a quantity that evaluates the goodness of the action that has been selected. Okay. So here in this case, the actions that we are selecting in the state value function was some arbitrary action to move from state S to S prime and S prime to S double prime and so on. But now in the action value function, it's a it's slightly different. So you are in state S, you want to move to state S prime and then S double prime. So the first action that you take is fixed. Okay. And after that, whatever action you take, let's say 2 prime and so on. This is uh, this is arbitrary. But what I'm fixing is this action that I've selected in the first at state S. So I'm basically estimating how good it is for the agent to take action A at when it is present in state S. Okay. So this is the another aspect of this is another aspect for uh, of the full RL that we are defining. Okay. So this is the value function part. Okay. And then before MDP, I should no, it is that. Yeah, before MDP, I should cover the return. So return is basically defined by this quantity. You can say it like this. Okay, so what we are looking at is basically the cumulative. I'm trying to not only optimize the immediate reward that I get, but rather look at the cumulative reward that I should optimize in order to uh, have a better, have the optimal policy. Okay, so this is what we mean by return. So a reward is something that is immediate. So the agent takes an action, it gets an immediate some feedback from the environment. That is the uh, that basically measures the goodness of the action that has been taken. So return is different in the sense it is looking at more on the longer run. So it's trying to reach the objective in this case. Okay. So this is the return function. So here we call this as the total return, which we're trying to optimize. Another variant of this is pretty popular. Uh, this is known as the discounted return. Okay. So this looks something like this. Okay. Okay, so here we have a, new parameter which we call as the gamma parameter. So this gamma parameter is known as the discount factor, and this thing is the discounted return. So this discount parameter, what it basically looks at is it's basically the reward that you're getting in the near future. It's placing more importance on the reward that you're getting in the near future than the reward that you're expected to get in the far future. Okay, so basically instead of giving some sort of an equal importance to all the all the rewards that you're expecting in the future time steps, so I'm trying to basically learn because most real world agents don't have the that far vision or that far sightedness. So you basically try to optimize in some nearby like some local future that you can see ahead. Okay, so you're trying to give more importance to the near future rather than the far future. Okay, this is the idea behind the discounted return. So this discount uh, factor is between 0 and 1. So this 0 indicates nearsightedness. This is the farsightedness. So in class, professor had given the example of earth, heaven, and hell. So can probably go back and uh, have a look at it if you want to have a clear understanding of what this. If you're still not clear with the discounted return part, okay. And yeah, there are a bunch of uh, other returns. One of them that sir mentioned was the average return. So yeah, I'm not trying to optimize the cumulative reward, rather the average reward in this case. T. And if the time horizon is infinite, I essentially take limit as n tends to infinity. Okay, so this is the average reward return. Okay, so so far we have covered all the components of what we have to define the MDP. Problem. Define the MDP, which will be used later in the RL course. So MDP basically uh, stands for Markov decision process, and it has two uh, strong assumptions, okay, which we call as the Markov assumption. So first assumption is that the probability that this quantity is equal to this quantity. All it says that this is the Markov assumption. All it says that you don't need access to the entire history of all the states and action pairs that you have reached so far, but only the latest, like the last state contains all the information about the history of all about all the previous steps that have been taken so far. Okay, and the second assumption is the stationary assumption. Okay, so these are two assumptions for the Markov, the two mark assumptions for defining an MDP. So finally, to end this lecture, I'll just write define the MDP tuple. So an MDPM is basically a tuple in reinforcement learning, which contains a set of all the states, set of all the actions, then the transition probability given the state action, the discounted parameter gamma. Okay, so this is the MDP tuple. So this, in this case, this probability, the states and the rewards are a joint distribution. You can write it in a separate manner. So if you were to split it out and write it independently, there's the states, the action, and you have the probability of moving to state S10 given condition on state S and A, and the reward dynamics look like this. Yeah, this is also an MDP tuple. Okay, so this was all. This was where Professor stopped in week 3, and yeah, so this was all that was covered. I think it's already time. I wanted to discuss the ungraded assignment, but I don't think I think we are beyond time. So I'll just quickly mark the answers. I don't think most of the questions were very complicated. First question is in full RL problem, which of the following is determined by the agent? So the agent only determines the action. It has no control over the rewards and the states that it has. So option 3 is the correct answer. Now here, which of the following statement is true about the RL problem? So our main aim is to maximize the current reward. No, we are trying to maximize the cumulative reward. Second, the agent performs the actions in a deterministic fashion. No, the agent is not deterministic, but rather stochastic. Third is we assume that the agent determines the reward based on the current state and action. That's incorrect because the agent also has access to the previous state and action. And fourth, it is possible to have zero reward. Yes, this is true. So this is the correct answer. Okay, I think this is a more of a mathematical question. I shouldn't do this right now. I don't have time. Uh, but yeah, all you need to do is you need to do the of like update the parameters according to the reinforce algorithm and determine the action taken at step t. So since this is a Gaussian distribution, so the theta parameters that you have in this case is your mu and the sigma value. Okay, so you need to find two separate updates, one for the mu parameter and one for the sigma parameter. So what is the answer? I don't remember exactly. So in this case, the answer is this. This one is the answer. Okay. Okay. This is an assertion and reasoning based question. Contextual bandits can be modeled as a full reinforcement learning problem. Yes, this is correct. The reason is we can define an MDP with n states where n is the number of bandits. Number of actions from each state corresponds to the arm, with each action leading to termination of episode and giving a reward according to the corresponding bandit and arm. Okay, so the assertion is correct, and the reason for this assertion is also correct. So option one is correct. Lastly, for discounted returns, we have this quantity. Which of the following best explains what happens when gamma is greater than 1? Okay. Theoretically, nothing can go on wrong, but this case does not represent any real world problems. So this is incorrect. First option is nothing. Gamma greater than 1 is common for many RL problems. No, it's not very common. The agent will learn that delayed rewards will always be beneficial and so will not learn properly. This is the correct answer. Okay, yeah, I think with this, we have covered all the assignment questions. I think I've covered everything that has been there for week 3. And I think we are a bit over time, but I think this is a good time to stop. If you have any questions, feel free to, contact me or put it in the discussion forum. We monitor it every week. And if not, we can end this session. Thank you for attending and happy weekend. Thank you. So you guys don't have any questions, right? I can end the meeting. Okay, cool.